Assalamu alaikum. Welcome to lecture 15 of natural language processing. So today we will continue with our discussion on vector semantics. So we were discussing how to learn representations for linguistic units. So learning representations. And we had talked about the distributional semantics hypothesis, which basically says that the meaning of words is determined by the meanings of the words that are in its context, that appear nearby it in running text. So that is the main idea behind learning representations for words in NLP. And the vector representations that are found are also often called, especially the dense forms, are also often called embeddings. So embeddings basically means that each word or any other linguistic unit for which you have a dense vector can be represented in space as a point. And multiple words would thus be points in space, or you can say they are points that are embedded in space. So that's where the name embedding comes from. So today we will discuss dense vector representations based on term document matrix, and then we'll move on to word or term by term matrix or term context matrix, and we will discuss the weighing schemes for these matrix. We initially discuss counting, and then we will discuss TF-IDF, and then we will discuss PPMI, point-wise mutual information, positive point-wise mutual information. And then after that, we will talk about another way of getting representations, which typically yield dense representation, which is word-to-vec. Okay, so let's get started then. So the whole idea was that we would like to represent words in a richer way that encodes or embeds much more information about the word. And we said that we will represent words as vectors. So a vector could be of several elements. It could be from 50 to hundreds and thousands of elements. So all of those elements of a vector would encode information regarding that word. And we would like to learn this vector rather than to hand code it or to do feature engineering, which is, of course, not always practically possible. So we started with dense. Okay, just before that, a couple of things. So generally, when we talk about words, which is the lexical unit in any given language, words have meanings, and usually meanings are also called senses in the linguistic sense. So a word may have multiple senses, even though spelling-wise they might mean the same thing, but they may have different senses. For example, the word bank may have different sense. It has the sense of a financial institution. It has the sense of the river bank. Similarly, you can think of word like live or live. Live, the verb live would be basically a verb that talks about life. And then, of course, live match is an adjective. So, and in English, and I think in many other languages, you usually have multiple senses for most words. So, and of course, there are relationships between senses. So relationships exist between senses, not words, because as I said, a given sequence of characters may mean different things. So we will relate senses rather than words. So relationships can exist between senses. And for example, there's one relationship called synonymy. Synonymy, so which is meaning that two words have similar meanings. In other words, if one word is used in running text, you can use the other word in that same place, and the meaning of the whole sentence would not change significantly. So those two words are synonyms. So things like car and, for example, automobile. So these are synonyms, meaning that you can replace one word with the other in most uh, running text without changing the meaning of the text significantly. So such words are synonyms, and of course, this is a relationship that exists between the sense car and the sense automobile. So to quantify synonymy, we can think of the notion of similarity. So the notion of similarity, of course, is commonly used in data science. Two objects are similar if their representations are similar in some way, and you can quantify them in various ways. Last time we said that in the context of NLP, if two words are represented or two linguistic units are represented as vectors, you can quantify the similarity using the cosine of the angle between those vectors, which is called basically cosine similarity. So cosine similarity kind of would quantify the similarity between two words. But oftentimes the relationship between senses are not just similarity. So they are more general. Uh, so they may belong to the same group or semantic field. So, and semantic field, of course, a group or context or whatever you want to call it. So for example, a nurse and a hospital are obviously not synonyms, but they're of course related, right? Similarly, a carpenter and the saw. By the way, saw is also a hyper polysemous word. So saw, of course, is the past tense of see, and saw, of course, is the noun, a machine that is used to cut wood. Okay. So again, these two are not synonyms, but they're of course related. And then even you can have things like antonyms. So antonyms, of course, the senses are opposite. So for example, good, bad, opposite senses. But still they are related. Uh, they belong to the same semantic field, in this case of antonyms. And then, of course, you can have various other semantic fields, the semantic field of positive words. By the way, this concept of positive word, negative words, and other emotional aspects of words is also called connotation. So words may have connotations. Okay. So, but the point that I wanted to highlight is that the more general term is relatedness rather than similarity in the context of uh, NLP. So we are more interested in relatedness rather than similarity. Why? Because whenever we are trying to deduce or induce the meaning of words from context, so for example, the example I gave before, nurse and hospital, nurse and hospital may be used together frequently in the same context. So they might appear close to one another in running text. So, but they are not synonym, but they are related. So in most cases, whenever we are deriving deriving meaning from context, it is not just similarity, it could be antonyms, it could be other semantic fields. So that's why we talk about the concept relatedness rather than similarity. And using that same thing, then we can use cosine uh, measure to quantify relatedness. So cosine similarity, the measure itself is actually quantifying relatedness rather than just similarity. Okay. All right. So now let's move on to learning vector representations. First, let's talk about sparse. And we talked about this last time, term, document. So term document matrix has terms on, you can say, as rows and documents as columns. And of course, for any corpus, the total number of terms would be equal to the vocabulary size. And of course, there might be several documents. So you have a 2D representation. So let's say, I think I showed this. So let's say your document D1, D2, and D3, and then you have some word D. D occurs, let's say 10 times, 15 times, and 20 times. And then let's say you have the word Lahore, which occurs 0, 0, and let's say 5. And then let's say you have the word science, which occurs, let's say 5, 0, and 0. All right. So of course, these numbers that I've written is the count. Sometimes in NLP, we also call it frequency, but I like to call it count because frequency sometimes may mean that it's normalized. So count of word in document. Okay, that is the weight or the measure or the quantity that's used in the matrix. So given this information, which of course you can say you have learned from the corpus, you can represent documents as well as words as vectors. Okay, so let's say vocabulary size is M, and let's say the number of documents is equal to N. So you have essentially an M by N matrix. Okay. So what is the, so if I talk about the vector for science, so this would be of dimension M, in this case, of course, 3, N, which is of course 3, number of documents. So in this representation, the length of the vector is equal to the number of documents that we had analyzed in the corpus. And of course, this, let's say I say science as the vector is basically 5, 0, and 0. Similarly, Lahore as a vector would be 0, 0, and 5. And let's say then we have D as the vector would be 10, 15, and 20. So this vector is more expressive. It has multiple values, number one, plus it is capturing or it's capturing the notion of the concept of words being used, similar words or related words being used in the same context. For example, in a given document, let's say a document which typically talks about science stuff would have science in it, but probably may not talk about Lahore, which might be commonly used in a document that is about, let's say, geography or let's say politics and so on. On the other hand, the word like D, which is a commonly occurring word in English, would occur almost frequently in all the documents. Okay. So you can then quantify the relatedness between two words by simply taking the cosine of those words, their representation. So for example, the similarity or the relatedness between, let's say, science and Lahore. So what would that be? You simply take the inner product of science with Lahore and then divided. Of course, this is normalized, not just the inner product. The cosine of the angle is divided by the length of Lahore and the length of science. So if you take the inner product of Lahore and science, you will get 0. Actually, there is no overlap in the two. So 5 occurs in the first position in one case and 5 occurs in the last position in the other case, right? So there is no similarity. You get 0 there. So, and of course, cosine similarity, since these vectors are always positive, non-negative actually, this cosine would only vary between 0 and 1. You won't get negative values. But in general, cosine of the angle would vary from -1 to 1. But in our case, you will only have values from 0 to 1. So 0 means that they are not similar or not related, and 1 means that they are highly related. And of course, uh, from a geometric perspective, this is the angle between the two vectors. Of course, the angle between two vectors, but to be normalized with the length, because vectors may be of different lengths. All right. So any questions? So, so we had used counts as the numbers in the matrix. It turns out that count is not a very discriminative measure. So you like something that is more discriminative. So for example, in the example that we saw, D, the word D occurs frequently in almost all documents because it's a common word. Okay? So, and of course, given whatever our task is, we may not be interested in the word D. We will be interested probably in the other words, like science and Lahore in this case. So we like to have a measure that is more discriminative. It will kind of reduce the impact of words like D and increase the impact of words that are more relevant or discriminative across the documents, like Lahore and science and so on. So the measure that is typically used for this is called term frequency, inverse document frequency. Term frequency, inverse doc frequency. So this is, of course, a very common weighing scheme, very popular in IR, information retrieval, and web search. So let's discuss that. As you can see, so TF-IDF of, let's say, the word science in document D1, or in any case, in general, the term T in document D. Let me write it in more general sense. So term T in document D. So this is the value in the matrix. A term T in the document D, this is a value in the term document matrix. So how do you compute this? It has two parts. You have a term frequency that is multiplied with the inverse document frequency. That's why you have the name TF-IDF. Okay? So TF of term in document D. Of course, there are a number of ways of computing this. I will mention maybe one or two. So term frequencies can simply be the count of the term T in D. Okay? But usually this count, since you may have documents that are long, you may have documents that are short, we would like this count to be normalized. So although sometimes people still use raw counts, but to normalize it, uh, again, there are a couple of ways. One way is to normalize it with the max count within the document, max within D of C, T, D. Okay. So if we are talking about a specific document, let's say document D1, ऊपर हमने D1 लिखा था, D1 में आपके पास पहला वर्ड D था, which is 10, दूसरा वर्ड था आपके पास, let's say science, science 5 था शायद, और then sorry, दूसरा था लाहौर, and तीसरा of course science था 0. So इसमें the maximum, what is the maximum number of counts that is occurring, which is 10. So in the denominator, we will have 10 always, so that in any case, this ratio would have a value between 0 and 1. So when you count, when you compute TF for the word D, 10 would be divided with 10 to give you 1. Otherwise, it will have a value between 0 and 1. Okay. So this is one way of quantifying the TF. The normalization, in this case, I've done with the maximum count, sometimes also with the length of the document, the number of words in the document. So that's also sometimes used. So in other words, so TF, T, D is basically C, T, D divided by number of words or terms in D. So this is another way to compute TF. Another way, which is also given in the book, is, of course, I would say the first one that I mentioned is more common. As far as I know, the others are less common. So TF, T, D, you can take the log of the count. So of course, log kind of squashes the count. So at high values, it increases as, for example, depending on what log you're using, log 10, you can use log 10. So after 10, 10 increase of 10 would just be increase of 1. Okay. So so you can do log of count T plus D, plus sometimes you just add a 1 there, because log of 0 is not defined. So if a word occurs 0 times, you just add a 1 there to avoid an error. So these are 3 ways of computing TF, which basically is directly related to the count of the word T in document D. Of course, with some normalizations. Normalization, one is with the maximum count of words in that document. The second is with the number of words, total number of words in the document. And the third is of simply the raw count, just take a log of it. So what is IDF? IDF of a term is just defined for a term over a corpus. Okay? Is basically the inverse document frequency. So we had n documents, right? And we have document frequency of T. So document frequency, what is document frequency? Document frequency is the number of documents that contain this word T. So if this word is contained in all the documents, then the document frequency would be n. Okay? And of course, inverse, ulta kar dein, so that's frequency, so that's why this is called inverse. So in practice also, isko zyadatar commonly so this is done, there's a log over it. Log le lete hain again to squash it. Okay? So this is the inverse document frequency. So if a word occurs in all the documents, what happens? So we have log n divided by n, which is log 1, which is of course 0. So it reduces the impact of words that occur frequently in all the documents. Okay? So, and if a word occurs in a fewer documents, then of course this term would be higher, or it magnifies its impact. So overall TF-IDF of a term D in document, term T in document D is basically, if I use the popular, so count of T, D divided by max in D of the count of T and D. Okay. Then multiplied by, of course, log of N divided by DF of T. So this is how you compute the TF-IDF of a term in a given document. And of course, as you can see, for any given document, if you want to find TF-IDF, you need to have all the other documents also, because IDF depends on the corpus. It doesn't depend on just that document. It depends on the corpus. Okay? So we need to have the corpus available with us. So this measure would be somewhat more discriminative as compared to raw counts. And this is commonly used for representation in NLP as well as in IR. But usually this representation is sparse for most real world data set. So why is it sparse? So usually we will have, let's say M is a vocabulary, typically it will be in the thousands or hundreds of thousands. And let's say N is the number of documents, depending on your application, this again can be in the thousands. Let me just write hundreds here. Okay. So you have, let's say, 10,000 distinct words and hundreds of documents, let's say 100 documents. So not all those 10,000 words would appear in all those 100 documents, right? So they will not appear in many documents. So you will have, for example, if I have some word like, so for example, lackluster, this is a word. So this may occur only in very few documents. So there will be a lot of 0, 0, 0, 0. Maybe one document has 1, 0, 0, 0, 0, 0, and maybe another document has 2. While on the other hand, the word like A might occur in many documents, 15, 5, 3, 10. Of course, these are raw counts, 5. But there are many such words that occur infrequently. So lackluster is an example. You can think of something else like, of course, in different contexts, not all words are used. So you can think of, let's say, the word gene in biology. So this might be used in only maybe one document. Okay? So lots of zeros. So in this case, if you have the representation for gene, so this is 0, 0, 0, 0, 0, 0, and maybe just 2 there, 0, 0, 0, 0, 0. So this is, of course, sparse. Sparse. Okay. So only few values are non-zero. And as such, these representations are sparse. And of course, they are also very long. Of course, for each word, the length would be equal to the number of documents. And for each document, the length would be equal to the vocabulary size. Okay. Okay, now let's move on to another, which is term matrix. And in general, let me start with term context matrix. Okay. So again, we have a 2D structure. We have terms as rows and context as columns. So context could be any unit of interest of running text. So if we think about the previous representation that we talked about, where we had term document, So document was our context. So in that sense, term document is also an example of term context matrix where a whole document is the context of a given word. Okay? But usually, especially for vector semantics, we will think about contexts that are of smaller sizes, not whole documents. So they could be paragraphs. So context, so can be in general docs, of course. They could be paras. They could be sentences. They could even be sections, depending on if your document has sections. There could be other things as well. Tweets, for example. They could be, if you want smaller units, they could be clauses, and so on. Okay? So we can define smaller contexts for each word, depending on our application. So, but we will, of course, we can use that and whatever context we like, depending on our application. We can generalize this to term matrix, in which the context is a word, the context is a window of words around the target word. So for example, let's say I have the sentence, Lahore University of Management. Okay? So let's say I define a context of size +1 and -1 words. Okay? So meaning that if I take any word, let's say I take this word, Lahore, university. So this word, and I say the context for this word is just one word before it and one word after it. So in this, the context of this word would contain the word Lahore and management. So in other words, we are defining context based on the target word, not on some linguistic concept like a sentence or a clause or a paragraph. And we define it with the length of a window after and before the word. So this is, of course, a much narrower context, and this is commonly used. So if you do this, then the matrix that we get is simply the term matrix. Why? Because let's say I have the word, let's say Lahore here, I have university here, and I have management. These are words. And as columns, you also have the same words, Lahore, table again. Okay. So Lahore, and then we have, of course, university, and then, of course, management. So as columns, you also have those same words. So okay. So now, so let's say if you talk about the rows as the target word, so then we'll take Lahore and see if Lahore occurs in the context of Lahore. of course, this is the same word. So this would, if you count it as the context, it will always occur. So this is, of course, trivial. So the diagonal of this matrix would always be the number of times a given word occurs in the whole corpus. Okay? But let's say if I say Lahore and the context is, so of course, this is, let me just say 0 laga deta main Lahore ka, just to distinguish it. And what about Lahore and management? So does management occur in the context of Lahore in this small corpus? Yes, just once. And what about Lahore occurring in the context of Lahore management? I didn't write the other word, so it's actually university. So Lahore, so of course university occurs once. And then of course management, if you take the context of just one word in front, so this would be 0 and so on. Similarly, for university, does Lahore occurs in the context of university? 1, I put manage university 0, and then of course here 1 again. So of course you do this for all the words in the corpus, and you do it for, let's say the corpus could be huge collection of data or collection that is obtained from multiple documents, for example. So here, of course, I'm writing raw counts. And of course, since we had just one sentence, I'm getting 1 values, but these values would be higher. So if you notice this, this matrix, this is actually a co-occurrence matrix. And the values we have are essentially the counts. So the number of times that, for example, management occurs in the context of Lahore, okay? Or the number of times science occurs in the context of management and so on. And we can create such matrices for different context sizes. So usually in practice, we will have +4 and -4 word context. So you can have more or less as well, but 3, 4 is common. All right. So now, again, we have created a matrix. We have created a vector representation for word. If you consider the row of any word, let's say row of Lahore, right? So this would be a vector. So 0, 0, 0, let's say 1, 0, 5, 0, 5, 0, and so on. And what would be the size of length of this vector? Basically M, which is a vocabulary size. Remember, the number of rows and number of columns is equal to M, which is a vocabulary size. And of course, vocabulary size can be large for many applications, easily in the thousands of words. So here again,
sir,
and the question?
yes, sir, इसका जो length होगी वो number of documents नहीं होगी instead of vocabulary size.
No, in term matrix, length is the vocabulary size. So remember the context now is words.
Okay, sir. सही sir.
वो जो पहले मैंने किया था वो term document matrix था, उसमें length n थी, which is number of documents. In this case, the length of the vector is equal to the vocabulary size.
और सर जैसे आपने 5 लिखा है तो ये 5 क्या रिप्रेजेंट करेगा? मतलब जैसे आगे 5 वर्ड्स एक जैसे हैं या क्या चीज 5 डिनोट करेगा?
Exactly, इसी तरह. मतलब context window आप define करेंगे हर एक word के इर्द गिर्द. So in other words, let's say मैंने जो rows में लिखे हैं वो आप समझ लें target words हैं. rows are target words और anchor words, ठीक है, और columns में are context words in the context of a target or anchor word. And of course, this context is defined as a window. ठीक है? This point clear?
यस सर। सर तो फिर एक ये मैट्रिक्स भी स्पार्स होगा क्योंकि जो भी हम वर्ड चूज करेंगे तो उसके अराउंड +-4 ही मतलब वैल्यूज अकर करेंगे, उसके अलावा तो सब जीरो ही होगा। Am I right?
Exactly. So this would be even sparser, I would say, because the context is smaller. इस context को small करेंगे तो obviously उस context के अंदर थोड़े ही words आएंगे, ठीक है ना? So you can think of examples like, for example, mm, so for example, word like D. So D is a determiner, right? So this would often be used commonly with words like nouns. So the chair, for example, or the house, or whatever. Okay. So, and also, uh, so you can think of words like, uh, so one thing that is kind of, you can infer using the window length. So window length, as I said, is plus W and minus W words. Okay. W, of course, could be 1, 2, 3, 4. So if W is small, let's say you just take a small window, +1, +2, or plus 2, or -2, or +1 or -1. So usually you will be capturing syntactic relationship, or syntax is also related to grammatical. So this would be kind of more highlighted. So मतलब syntax में क्या होता है, जैसे मैंने कहा कि the determiner हमेशा noun से पहले आता है, house for example. So इस तरह की relationships आप ज़्यादा capture कर लेंगे, और they will be prominent. ज़्यादा का मतलब they will be prominent in our representation if your window size is small. But as you increase the window size, then greater semantics information is also captured. So as window size increases, so so basically greater semantics are also represented. ठीक है? So of course, इसमें example आ सकती है. Let's say you are talking about some camera or some product review. So you will have in a product review a discussion of, let's say, camera. You will have lens, for example. You might have focus, for example. So these words may be used if you increase the window size somewhat. So now you're capturing greater, you can say, semantics or semantic fields information. So they are all of this is talking about but semantic field of camera. Okay. Similarly, if you have documents about biology, you might have gene, DNA. Of course, you won't have a sentence that say gene, DNA together. DNA. So you usually had DNA and gene, of course, maybe in the same sentence or a few words apart. They will not be adjacent to each other, because of course you are writing proper English. So as I said, if the window size is smaller, syntactic information is retained or prominent in the representation. If you increase the window size, then semantic information becomes more prominent. Okay. So typically, as I said, window size +1, -1 is not used. We usually use window size of +3, -3, +4, -4, +5, -5, maybe even up to +7, -7. ठीक है? Okay, so we were talking about term matrix, and so far we have used the raw counts. So as for the term document matrix, there also raw counts were considered to be less discriminative or effective. Here also, another measure is more commonly used, which is called a positive point-wise mutual information, of course, PPMI. So instead of using raw counts as the values in the matrix, we will use PPMI. So PPMI is actually related to correlation. Of course, it's based on mutual information, you can say, but the formula is similar to correlation. Of course, you take the log of it. So PPMI of word I and word J. So word I is the target word J is the context word. ठीक है? So इसमें मैं इस तरह भी लिख सकता हूँ word and C कर देता हूँ. ठीक है? So of course, both of them are words. W is the word and C is the context word. Of course, the context word C that occurs in the context in the vicinity of word W. Okay? So this is defined as log. You can take log base 2 if you want, but you have to be consistent whatever base you use. You can use 10 as well if you want. Commonly used base 2. So this is basically given as probability of the joint word and C divided by the you can say the separate probabilities, probability of word, probability of C. So basically the ratio of the joint at the numerator divided by the individual probabilities of W and C. And of course, all of this, we take a log of it just to squash the increase of the value. So of course, if you look at the expression, you have the joint up there and you have the separate probabilities below there. If this value is 1, we can say that this word and this context word are independent. Because from probability theory, we know that probability of WC is equal to probability of W into C. When would this be? When W and C are independent. Independent. Okay? And of course, if they are not independent, then this would have a value. Okay? So it turns out that we are not interested in negative correlation. Of course, if probability of W and C is less than the product or the probability of W and C, then they are negatively correlated. So negative correlation is not of interest to us in most NLP tasks. Why? Because we are interested in whether a particular word C occurs in the context of W. If it occurs less in the context, to capture by that other word at some other place, where C is W and W is C. You get that point? So of course, we are having the whole matrix. So W, for example, W, let's say, is Lahore, and C is, let's say, science. So you will be computing in one case, and in the other case, you will be computing W as science and C as Lahore. Okay? So both of them would be captured. So if there is a negative correlation, it will be captured in the reverse scenario. So for any given scenario, we are not interested in a negative correlation. So that leads us to the positive. So far what I've written here is, so actually what I've written here is just the point-wise mutual information. Okay? which can give you a negative value as well. Okay? Of course, a value that's less than, we are taking the log of it. So if you have a value that's less than 1, you get a log which is negative. Okay? So what we do is we just retain the positive value of it. Positive PPMI would thus be simply the max of PMI and 0. Okay? So we do not keep the negative value. So if a value for any pair of words W and C is negative, we just replace it with 0. So this now is the weighing scheme that is more common for term-term matrices or for term context matrices where the context is much narrower as opposed to the whole documents. Okay. So by the way, what we have computed is probability of W. We need to compute this probability of WC, right? You can use, of course, you can write this as what? Probability of word given context, okay? Then probability of context, okay? If you do that and put it in the formula, what do we have? Probability of W given context, probability of context, denominator में क्या था? Probability of context, probability of W. So context की probabilities cancel हो जाएंगी. So this simplifies to probability of W given context divided by probability of W. So you can also write it in this way. Okay? And of course, from language modeling, probability of W given context, if you use MLE to estimate it, what is this? The count of W and C divided by the count of C. Okay? And similarly, you can estimate probability of W. So probability of W would be the count of W divided by total number of words in the corpus. That would be the MLE estimate. Of course, if you want to do add K or add 1 or even knee smoothing, you can do that as well. So any questions? So here again, we get a sparse. So sparse representation. So there will be many zeros. So there will be many zeros. Why? Because of course the context is narrow and not all words are used in the context of every word. Okay. So again, we have a sparse representation, but still is a representation that captures meaning. And that meaning, as I said, can be controlled somewhat, of course, not, you can say, in a black and white fashion between syntactic information and semantic information by varying the size of the window. And then, of course, we can use cosine to determine the similarity between two words. So, okay, so that was some sparse representations. So let's now move on to dense representations. So we have about 15 to 20 minutes. So we will start this and maybe we'll slightly continue it next time. So of course, sparse representation means that you have lots of zeros and you have lots of, the vector length is very large, especially for word matrices, co-occurrences matrices, vector length is equal to the vocabulary size, which is going to be huge for many applications. So we would like to have smaller, or you can say shorter, vectors. Why am I having spelling mistakes? Shorter vectors, but with few or no zeros. So that's why what we mean by dense. Okay. So let's say even if you have now the vector lengths could vary from, let's say, around 50 to about 1,000 words. Sorry, 1,000 elements. So this is typically used in practice. So instead of having 10,000 vector length, we can have just, let's say, 128 as a vector length. But all of those 128 would have non-zero values. And as such, more information is packed into a smaller length vector. So that is, of course, the idea of a dense representation. And of course, if you have dense representation, your computational efficiency would also increase. You will have to process fewer number of elements. So a matrix, a vector multiplication of 100 and 100 is much more quicker as compared to 10,000 by 10,000. Of course, you can use some techniques for sparse representation in programming, but still it's going to be a huge overhead. So that is one of the motivations for dense representations. And then now let's talk about a popular technique for generating dense representations, which is actually different from the ones that we saw already. So this technique, and this, I would say, technique revolutionized NLP in the last 10 years. Word2Vec, so this was proposed way back in 2013. So Word2Vec, basically, as the name suggests, you map a word to a vector. And of course, that vector is a representation of that word. And they use these people used a machine learning approach to learn the vectors. Of course, in the previous case also, you can call that machine learning as well. PPMI को भी आप machine learning assume कर सकते हैं. But here, the machine learning is more direct. So we basically use supervised learning. But as we will see, we don't really need labels for supervision. You can get the labels automatically. So in this case, it's called self-supervision. Okay. So let's now move on to what is the idea. And actually, these people propose two techniques for the representation, two ways of generating these representations. One is called a skipgram, and the other is called a continuous bag of words. And of course, these names are non-intuitive. They are not very intuitive, but that's how they have used it. So continuous bag of words. Both of them are actually very similar. They just propose two ways. So we'll start with discussing the skipgram representation or skipgram approach. Okay? So what is the idea? So we want to build a classifier I'm having too many spelling mistakes today. Classifier. Okay? To build a classifier to predict the context word given a target or /target/anchor word. So this is, of course, the approach used for skipgram. So remember, so prediction. So we are learning a classifier. We're learning a model that when given a target word, it will predict the probability or probabilities of all the words that occur in its context. So for example, let's say I use the word science as a target word. I input this to the classifier. The classifier would be able to predict to me whether probability of Lahore occurring in the context of science, probability of D occurring in the context of science, probability of live occurring in the context of science, probability of other words like computer in the context of science, and so on. So input is Lahore, output could be any of the words from the vocabulary, of course, with the probability distribution. But the interesting thing is, this is not the goal of our task here. Of course, we are learning this model, but we are learning this model, and after we have learned this model, we simply use the weights for the word Lahore, Lahore, left side, science, for the word science as a representation for this word. So remember, if you talk about logistic regression, and later on, actually, this we will discuss in terms of neural networks. So that's why we studied neural networks before. So the weight vector associated with this word Lahore would then be the representation for this word. And we go through the building of the neural network or building of the classifier just to learn that representation. So of course, so in the example above, if you input science, and let's say you have a huge corpus of documents and you take science as a corpus word, and just intuitively, so which word is going to come frequently? What is the probability of Lahore given science? I mean, I just intuition, of course, this might be relatively high, yes. The would also be high, right? Live might be relatively low. So why would you want to use live with or live adjective with Lahore or with science? And of course, computer might be quite high with science because computer science is occurring almost together with science in most corpus that talk about science, and so on. So you get a distribution over the words that occur in the context of word science. So this approach where you have an anchor word and some context word, and you're trying to predict the context word given the anchor word, is the skip-gram approach. Okay? So we are going to predict a word from the vocabulary. So essentially we have a multi-class but later on we'll see that we'll change this to a binary class classification problem. But essentially right now it is a multi-class classification. Given Lahore, we want to predict whether, or we want to predict the distribution of all the words that occur in the context of the word science. Okay. So it is multi-class. So how many classes would there be? M classes. M, of course, is the vocabulary size. Okay. And of course, now the question is, how do we represent each word at start? So, for example, we have the word science. How do you represent this at start? Of course, as an input, of course, later on we'll have some weights that will associate with science that would be its embedding. So initially we use the one hot encoding for representation of words. What does this mean? So you have a vector of length m, which is vocabulary size, and you have a 1 for the position for science. So let's say if I have just 3 words, the, Lahore, and science. So if I want to represent the word Lahore, what the vector will be 0, 1, 0. So this is of course Lahore. So if I want to represent the word the, this will be 1, 0, 0. This is of course the word the. And if I want to represent the word science, this will be 0, 0, 1. Okay? So this is the one hot encoding. So we can at start represent each word in the vocabulary in the one hot encoding approach, in which we have just one at the position that we have defined for a given word, and the rest of the words or rest of the positions will have a value of 0. Of course, this is sparse, as you can see, but this is just for starters. So we have represented each word as a vector at start. So next thing is we need to create a training data set. So how do you create the training data set? Remember, we have to have an input word, which is the anchor word, and then you have to have the output word would be a context word to that anchor word. So we'll build this training data set from running text. So no explicit okay. So let's say again take the example of my running text is Lahore University of okay. So of course, this is just a small example. And let's say you have to define a context window also. So again, let's say I define a context window of +1 and -1 word context. And now I'm going to write input, output, word pairs. So let's say if I take Lahore as input, what would be an example of its context word? Of course, university is a context word, right? Output for this. If I input Lahore, then university should be an output because it appears in the context of Lahore. Of course, there are no other context, but there's nothing on the left-hand side of Lahore. So we take the next word, university. So what is a context word for university? We have, of course, Lahore. And what is another context word for university? On the right-hand side, Lahore University of. Okay. If you take off के लिए आपके पास Lahore University of, so you have university on the left-hand side of, and then we have management on the right-hand side, and so on. So of course, so all of these are now training examples, input-output pairs that you have directly obtained from running text. No one did any labeling. Labels were already found in the running text. So that's why this is called self-supervision. So there isn't any external entity that is providing supervision. You already have supervision within the corpus that you are using. Sometimes people say this is semi-supervised learning. This is incorrect. So semi-supervised learning is something else. So it is supervised, but the labels are already present in your corpus. So you just to make it further distinction, you can say it's self-supervision. No external entity is required to do the supervision. So is this point clear? The training data? So we're also running out of time. So we have the training data now, and now we have to look at the neural network model that is used to do this classification. So we will have an input layer. So input layer, of course, its size would be M, because remember, each word is one hot encoding, its length is M. We will have a hidden layer. Usually we can have just one hidden layer, and its size is, let's say, let me use a notation H. And of course, this H is generally less than M. And then we have the output layer. Output layer size is also M. Remember, this was M class classification. Remember? We talked about neural networks in the previous lecture. So if you have an M class classification problem, we have an output layer which has M nodes. Each node corresponds to a specific class. And of course, you will use the softmax function to process all these nodes. Okay. So, and then of course, you will have weights between these layers. And I think I will probably start from here, and maybe I'll start with just copying this stuff from this lecture, and then we move on to the weights and how those weights actually represent embeddings. Okay, any questions? Any questions? You are supposed to start working on a project soon. I mentioned that in the last class, please form groups and send your group names to the TSR. I wanted to upload the handout today, but I think it looks like I will be uploading it tomorrow. But you can at least start with the group formation as soon as possible. And as I mentioned last time, the project this year would be primarily an implementation of some recent paper, re-implementation of some recent paper, or some work that has already been done. Although there might be slight exceptions, but those exceptions will be based on discussions with each of you. The default is you pick 2-3 papers and select one paper and re-implement it. So maximum 3 people within a group. Of course, if you want to do it individually, that's up to you. So please at least start working on the group formation. And if you already have some ideas of some paper, the paper, of course, should be in the past 5 years. You cannot re-implement something that was published like 20 years ago. And of course, it has to be NLP. You cannot bring me something from computer vision. Okay. All right. Any questions?